Our speaker tonight is Luke Deasy. He is the founder and managing director of Copper Coast Renewables. It's a sustainable energy company that specializes in solar and wind energy solutions for businesses and communities. Luke is a chartered electrical engineer with an extensive experience in managing complex and large-scale projects around the world, to be honest. Recent awards given to Luke include the Engineering and Construction Professional of the Year and the Overall Young Professional of the Year, awarded by the Lincoln Irish Early Career Awards. And more recent again, these are all the last couple of years, guys. The National Renewable Energy Entrepreneur of the Year, awarded by the All Ireland Business Foundation. And I believe there are more. I'll leave Luke introduce the topic himself, and please enjoy. No, to you.
Cheers, Jim. Hello, everybody, and thanks a million to Engineers Ireland for the opportunity to present on this project. So, this project is an off-grid solar island presentation, and it's the only fully off-grid island in the country powered by renewable energies. I'm just going to do a quick overview of the presentation. So, we're going to delve a small little bit into Copper Coast Renewables and what my company does and our services. The next section of the presentation will run over the project overview, the location, some people in the crowd here already know, and challenges and solutions and how we overcame some of the issues on site. We'll then spend a bit of time in the actual technical details of the project, the equipment that was selected, why it was selected, and how it's connected. And we then have a brief video of the installation process as the completed installation. I'll talk over that just to explain what's happening. Then we have a section on benefits and impacts, and a section at the end for questions and answers. So, about us, Copper Coast Renewables, founded in March 2023 by myself, and our idea is to lead the way in change from fossil fuels and transition to a green energy economy for all of our clients. The idea is that we'll take it from that first phone call all the way to end of life and decommissioning 20, 30 years later, or upgrading, so that we can be a net zero partner for our clients rather than just coming in, doing a job, leaving, and having no support afterwards. Our services include design and consultancy in solar, batteries, EV. We're starting to break into heat pumps now in the next 6 months, so watch out for that. We also do energy management. We're registered SEAI energy auditors, so that we can enter into your businesses, review all your processes and procedures, and put together a net zero plan for you guys over the next however long of a duration you want to commit to. We also offer finance solutions through one of our partners for anybody that has an issue with CapEx, and with the payback for renewable energies these days, it's pretty decent setup. The next slide is kind of taken away from me there by Jim in the last one, which is just running through some of the awards. So I might skip through that since it's only already mentioned, and get into the actual project itself. So the project itself is based on Roaringwater Bay, just outside Schull, and it's based on Horse Island. It's an island that has changed hands many times over the years. It originally started as a copper mine, and there was at its peak in the 1890s, there was 137 people living on the 154 acres mining copper. In its more recent years, it has changed hands numerous times since the 1980s, but the main bulk of infrastructure was put in the early 2000s by the German owner at the time. How I came into this project is this island changed hands in the middle of COVID. It was bought over by a person from Cyprus in the middle of COVID, and I came into it then in April of this year. There's 7 homes on the island. There's a gym, a helipad, its own water source. It was originally back in the early 2000s powered by wind turbines. and batteries with backup diesel generators. At one point, they was looked at to put a distillery, Roaringwater distillery, on the island and run out an ESB supply. So there's actually no ESB supply out to this island. It's been 100% off grid since the mining days, and it has never had a power supply. That planning permission never happened, and neither did the grid connection. So it's one of those few islands that's been inhabited and off grid with no power since day one. Now there's 7 homes on the island. All the houses, there's no oil or gas. They're all electric heat pumps for heating, underfloor heating to keep the damp sea air and moisture from the buildings. You can imagine now what that's like in the middle of winter. It's not exactly the most hospitable place. There's 2 permanent residents on it. There's actually a herd of alpacas, and there's, I think, 12 dogs that love chasing any vehicle at all that they can for entertainment. It's accessed via boat. For the last 3 years, last 4 years, sorry, the wind turbines have been failed and fully decommissioned, and it was running on diesel generators. So 24/7 running on diesel generators. There was 3 diesel generators in case one failed, and then another backup in case another failed, just to keep the heating on. And there was a barge purpose bought to ferry out the oil tank, or the diesel tanker. That's how they were getting the diesel out to the island. So the existing infrastructure there, as I've just been through, and that's kind of how it was powered. The wind turbines, there was originally 7 2.5 kilowatt wind turbines on it, and they were great, and they were working away fine until they all failed. They just hit end of life, and there was issues with getting planning for more wind turbines to be re-put up there. So when the client approached myself in April, he was looking for alternative solutions. So some of the challenges were obviously the location and not being able to put wind out there due to planning concerns. Another one of the issues was it was running on diesel generator 100% 24/7, but there was batteries left over from the wind turbines. So there was wind turbines running through, charge controllers, and they were charging deep cycle marine batteries. They're big 80 kgs each. So they were powering the island with diesel generator backup. But once the wind went, the charge controllers were never recommissioned to run directly with the generators. So when we got approached in April, the first thing was phase 1 of this was to get the existing batteries back up and running so that the diesel generator would be reduced usage. So the idea was get the batteries back up and running, use the diesel generator to supply the load and charge the batteries. And then once those batteries were charged, kick off the generator and power the island on batteries. So we managed to, under phase 1, we managed to take the diesel generator from 24/7 to only 8 hours a day. We were able to charge the batteries and get the old charge controllers up and running. Some of the batteries were end of life because they had been discharged beyond recovery. So we didn't replace them because we knew we were doing a phase 2 with solar. We just recoupled them and got them, recommissioned the system and got it up and running with the new settings. Another issue on this was that timelines. We wanted the end solution as quickly as possible to try and cut down the extortionate diesel bills that were going on at the time. So that was part of the reason for the phased approach, was number 1, get the old system up and running, and that gave us then time to evaluate different systems. The water on the island is actually there's a freshwater river underneath the island, believe it or not, and that's actually how they have fresh water. So one of the approaches that we were going to put in was an on-site 5 or 10 kilowatt hydro pump and slot it in to one of the wells. There was issues with that on number 1 timelines, and number 2 on environmental when we looked at it. So that's not completely gone away because that river is there and it's constantly flowing. It would leave the generator working even less, and we have the percentages of how often the generator is running later on in this presentation. But the time it was going to take to do the excavations, fit the pumps, or get the pumps that were required and fit them, it wasn't going to be in 2023. So one of the quickest and easily deployable renewable energy sources is solar. It's readily available. There's stocks in Rotterdam of solar panels, inverters, batteries. And that was how we ended up coming to that conclusion. So we had looked at numerous options. Wind would have been preferable, but when you can't do one, you just go to the next on the list, evaluate it through, and that's how we ended up with solar. One of the difficulties, of course, with solar is it needs to be mounted on a roof or on the ground. Now, the central distribution point of this island we're going to see in a second, but it was the main cattle shed, I suppose, the old cattle sheds as they were transitioned into work sheds there in about 2012. So that was where the main power distribution points were, and that fed out then to each of the homes. So for us to do solar on the homes, we would have had 7 or 8 different distributed solar systems, all feeding individual homes rather than one centralized system. All those roofs face all different directions. They're not all facing south or not all facing east, west. So that was causing another issue. The last issue that we had with solar was you're building on an island, and an island is pure rock. There's very little topside. So to put in a traditional solar mounting system where it's ballasted where it sea piles into the ground and faces purely south was a challenge. Also the high winds. So there's very high winds. It's off the coast. There's very little stopping it. Next stop, America, I suppose, is the honest answer. So there's very little stopping the winds or shielding the winds. So you get massive gusts. And that was another consideration for when we're going to put the system on a ballasted concrete ballast and raise it up off the ground. Normally you have about 800 mil off the ground at the front up to kind of 2.4 meters at the back. So if the wind whipped around from any direction, it has the potential to lift the solar panels up. That was something we were trying to avoid, and getting concrete out to an island is not exactly the easiest thing in the world either. And I definitely didn't want to be standing there with sandbags and concrete bags mixing it. So what we actually came up, or sorry, one of the other things that we looked at while we were out there is the island is largely, I suppose, uninhabited. There's two full-time inhabitants, and then there's workers in and out nearly every day. But the main load is the heat pumps keeping on the underfloor heating and keeping the heating in the homes, and just to keep the damp out and keep them in the condition that they're in. So the load during the day across the 7 sites, you'll see it there in a while, is about 7 kilowatts. But at night time, or just before morning and at night time, you're up over 10 kilowatts. So the load is actually steady during the day. So one of the other evaluations that we came to was a solar system. Traditionally, most people would understand is that you would install a south-facing solar system. Now, a south-facing solar system actually has a massive peak in the middle of the day. It has a curve that goes up like that in the middle of the day. The problem with that is, unless you have massive load in the middle of the day, what are you going to do with all of it? Let's say your batteries are charged in the morning because it's the middle of summer and you don't need your peak in the middle of the day. So what a lot of people don't understand about solar is it works just as well if you position the panels east-west facing. They actually get less of a peak during the day, but they start earlier in the morning and they run longer in the evening. So if you have a more steady load profile, you can install what's called an east-west facing system. East-west facing system has the benefit of being linked like this, which you're going to see on the next slide. So it also means that there's less places for the winds to circulate around and lift up when you're installing in somewhere as open, I suppose, as Horse Island is. And that was kind of the challenges and solutions that we had to come up with. So the next section is more on the technical details, and I'll talk more about that east-west facing system here. So we evaluated numerous inverters and numerous different panels, and part of that came down to what was available at the time. I suppose the timeline on the project was as quickly as possible to reduce the diesel bills and the carbon footprint. So one of the better off-grid inverters is the Solex inverter. We were also limited to the existing electrical infrastructure, that we couldn't just put in 100 kilowatt inverters and push too many amps through the existing cables and things like that. So that was another consideration that we had to do. So that's what kind of led us on to 5 15 kilowatt solar inverters. They're hybrid and they're bi-directional. So it meant that we were able to couple the batteries on the DC side of the inverter. So what that means is it was one less lot of AC infrastructure, but also that the inverter or the battery's maximum output will be limited to 75 kilowatts. If we AC coupled the batteries, we would have had additional controls in there, which we didn't want. We tried to keep it simple. It's not the easiest place to get to when something goes wrong. So I'm a firm believer in KISS, keep it simple. So that was another reason that we focused on the Solex. They're tried and tested world over for off-grid systems, especially on the smaller scale. If you're, off-grid power plants are a different story, but for the loads that we're talking about here, they produced some of the best. We used some of the bigger PV modules because of the footprint we were limited to. We wanted to get a 100 kilowatt peak, which is the DC solar system size, and the AC solar system size was 75 kilowatt peak. You can see that there just in the center. Some people may ask, how did you put more DC into the inverters than the AC load that you have? So most inverters, you are capable of installing over 1.5 of the AC capacity. The reason for that is partly because we're not in the Middle East. So every piece of solar that comes down on the panels isn't always used. There's also an efficiency in the panels themselves. So what it means is when you're in the northern hemisphere or further in the southern, it doesn't matter. But as you push up towards the northern latitudes, you're getting less and less sunlight. So for your CapEx investment, you can take advantage of the inverter's AC-DC ratio and push up to 100. So we've 75 kilowatts of inverters, but we've 100 kilowatts of DC. So to get 1:1 ratio, we would have an extra inverter. But during the middle of winter, when solar production is down, we're not getting any advantage of that, but we've put all the CapEx in. And during the summer, we would be getting the advantage of it, but we don't have the load. So it's always a matter of taking a measured approach with the data that's available and then filtering your best usage case back into the data that's provided to come up with your AC-DC ratio to offset as much as possible the client's load. The reason we went with the 540 watt sharp panels is they're a very, very good module. They're newer technology. Most of the standard panels that you buy these days are 460 watt. There's another reason is that we were limited in available space. We didn't want to go digging fields or interrupting the existing landscape. So we actually took the tennis court. It hasn't been used since it was installed. It's perfectly east-west facing, and no one was going playing tennis anytime soon. So we went and we actually took the tennis court. So using the 540 watt modules gave us a nice footprint to fit squarely in the tennis court. You'll see photos and things of that in a second. The east-west facing mounting system is there. You can see it there where it's more like a tent. It leaves very little height for the wind to come in. And there's actually a 15-degree pitch on that, believe it or not. So both ways, it doesn't look like it there. But it means that system we were actually able to physically bolt down to the ground with chemical anchors. So we didn't need ballasted weights. We put in the extra chemical anchors to bolt the mounting system directly into the tennis courts. So it's another way of alleviating the wind. The 36 Solex triple power batteries match with the inverter. We could have got slightly different BYD batteries or an alternative manufacturer, but again, we would have been very little price difference by the time we had to go adding extra components. These plug and play straight into the inverters, and they're all managed through one system, one centralized control system, the Solex control system. Made it nice and handy. We actually have two number 88 kVA diesel generators and a 33 kVA diesel generator on site. They've had them for years. So what we did is we recommissioned the diesel generators. So we've got a dual auto transfer switch. So the way everything is set up, and we'll run through a single line drawing here now in a second, but the way it's all set up is site runs on solar and batteries as much as possible. If the solar and batteries can't provide the load, the diesel generator kicks in. If the diesel generator were ever to fail, there's another automatic transfer switch onto the second diesel generator. If that happens, the solar cannot come back on because we've had a failure on the diesel generator. If that diesel generator ever failed, someone can manually come up and turn on the 33 to just provide lights and essential heating to the 7 houses. So it just means there's triple redundancy. The solar has to go, or quadruple. The solar has to go, the batteries have to go, 2 diesel generators have to go, and we still had a third. So that's how it was all set up. The total system itself is 75 kilowatts on the AC side, 100 kilowatt peak on the DC side, and 200 kilowatt hours of battery. You'll see the load profile there in a second on the actual usage on site, but even at 10 kilowatt hours, it needs to be full. If the batteries are fully charged, it nearly needs to be 24 hours of darkness before they run out. So now we have a special condition set, which we'll get through to in a second, that we don't discharge the batteries over the final 20% to extend their life. So it means the diesel generator will kick on if the batteries ever get to 20% left in the tank. If the 2 diesel generator fails, we actually dip into the 20% reserve before we go to the third. Jenny. There was a bit of PLC programming and different things like that going on there to get it done, but it works the finest. This is the single line drawing. So I'm not sure how large that is on people's screens at home, but for the people inside in the room, sorry, I think I can move the mouse here. Right. Over here you have the batteries. So these are all the batteries, and they are this is the BMS, centralized an individual BMS for each battery. And then this is just a DC isolator here, just for in case you ever need to swap or change battery packs. Looped into the Solex hybrid inverter. Now, this is kind of where it starts to get a little bit confusing. So you actually have off every inverter a dual feed, one to a normal board and one to a essential power services board, an EPS board. So in a normal situation, or under normal designs, you would only have the batteries providing essential loads. Problem with an island is everything is an essential load. They can't operate. There's no grid. So normally you put batteries in just for emergencies or to take care of your loads. So what we've done is, you'll see here, we actually have a cable. This we've changed to be the main distribution board, which are 2 diesel generators here, and they come into this board. We're then looped out of this board back up here to this board here, which comes out of this board into the existing services board. So what it means is we can feed inverters straight in here. We can feed inverters straight into this board. We can back feed up here to come down here. We can also supply a battery through here. And the real reason it had to be done this way is, if the batteries get to 20% usage, the diesel generator kicks in. The diesel generator cannot supply straight through the inverter, through the normal input on the inverter. It has to come in through the EPS load. So that's why we have 2 separate boards. So the diesel generator can come in here and charge the batteries, while also exiting here to supply the load through these changeovers, with this switch here being open. It took a while to come up with the algorithm and the way it needs to be wired, but it's working quite well. And it meant we didn't need to change the client's existing distribution board. We just had to change where it was fed from with our 2 new panels and interlink them. We were able to reuse the client's existing auto transfer switches as well. So there's only 1 box here, but there's actually a second box to the way it was wired on site. But just for the presentation, I tidied it up here. So it just means that we can, when we have no solar over here and everything is dead, we can take these generators and supply the on-site loads, but also through this here, supply the batteries and charge them up. And you're going to see that in a load profile there in a second. Trying to think, yeah, so the only other thing that we have here is we have energy monitoring, so that we can see exactly what the site load is. It's more of the inverters do it themselves, because in off-grid mode they provide the full load to the site, but it was a check when we were commissioning that we had a physical meter we were able to go over to and look at, not just the software on the Solex inverters. I'm still a firm believer in having something you can look at when you're working on it, rather than waiting on a 5-minute refresh on the website to worry about the controls on the inverters. This whole system then is wired up to the internet, and we have a full control system of it. We can turn it on or off or change our settings, whatever we need to do remotely from, I can do it from my phone here or from the laptop at home. So it also means we can diagnose the system, and it means we can track its production on the solar against its model. It's very simple add-on. It's only a 4G router and SIM card rental for a year. So it's something that definitely, if anybody's doing solar systems, should be adding in. Should be adding in, because it means I don't have to drive down to Horse Island every time I get a notification on my phone, or any time that they're wondering what is the system doing. And that system, the owner has it, the maintenance crowd on site have it, the local electricians down in West Cork have it, and I can diagnose most things remotely. Normally it's a string issue, or it could be just that the inverters are one battery is fully charged. On these batteries, we actually had 2 banks of 8 and the rest in 7s. So sometimes we get a voltage difference error, but it's just because we have 1 extra battery running on the inverters. The inverter might have a red LED on it, it's still working perfectly, but we can then clear it remotely. It's just as it's getting actioned in the software upgrade with Solex, which is supposed to be rolled out next year. So that was the single line drawing and kind of how it's all connected up. Now I have 2 videos here. I'll just see, can I play them one by one? So here's the tennis court with the solar system installed on it. It's east-west facing. You can just see the cable containment coming out into a trench down there on the bottom left-hand side. The 540 watt module, as you can see, we took up 2/3 of the tennis court. That 540 watt module has allowed us to step back from that concrete wall. They were kind of using that as a paddle wall, I suppose, or that's what it was originally intended for. So that left us enough space then to still fit the 100 kilowatt peaks, and a step back for shadow in the evenings that comes off that wall. So we knew then part of the problem with a shadow is in solar, if you shadow one panel, you're shadowing all the panels in that string. They're like batteries that way. When you string them together, voltage drops in all of them, so you get less production. So you try and keep your shadowing to a minimum. You can see here on this video, the workhouses and things like that, where the connection is over here, and this was a trench that we installed between the two. Everything was ducted and weather tighted as well. We also have lightning protection installed off of these frames here. You can't see them here, but there's 4 lightning rods, 1 in each corner of the solar array, and then they're linked down to the main LV arc bar over here, which is already earthed and has been for years. So that's the solar panel systems. We just leave that video finish out, because you can see we shot it on one of the best days going. We just got lucky when we were commissioning it. Hasn't been so pretty. I've been back a few times. It hasn't been so nice in the last few months. So you can see how low the east-west system is to the ground as well. So how little wind is going to be coming into it. So it really did help us going on the east-west facing system. Just behind it there's the helipad actually, and actually just beyond them is where the wind turbines were originally situated, and just at the top of that kind of hill at the back of the video there. I'm just going to walk through then on the batteries and inverters. So with the batteries, I'm going to play on that. I'm not sure. I think if there's sound now playing in the back of that, apologies, there shouldn't be. But we've actually got 3 rooms of inverters, of batteries, 1 room of inverters. So they're the Solex inverters with the batteries and the DC isolator switches and the BMS controls. Just over, this is the 2nd room. Again, more batteries, and almost the last batteries. There's 3 more inverters, left inside in the 3rd room. Everything is wired then back to the main distribution board as per the schematic that I had. So there's the last set of batteries, 3 full rooms of them. It's nice, it's easy gear to work with. It's very well put together. Believe it or not, the batteries and the inverters are IP65 rated. Now we have them all indoors and all the rest of it, but if there ever was to be water ingress or any of the rest of it, they're all IP65 rated, which helps when you're offshore. Not a million miles offshore, it's only 5 minutes in or 10 minutes in a rib, but still we'll claim it as being offshore. Just there on this switch room, I'll just try and highlight this is the Solex kind of, I would say, the brains of the unit. This is your EPS box. And just here, these are your automatic transfer switches. Now, anyone that knows solar, when you're installing a grid connected solar, you would have G10 or EGIP protection. And when you're off grid, you don't need that because the only reason you need G10 or EGIP is for ESB protection. It's built there actually to protect the ESB cables coming into people's sites rather than protect the on-site network for clients. So here we didn't have any ESB connection at all. So we didn't have any G10 or any EGIP. So just in case anyone doesn't see it there. These isolators up the top are the isolators, 1 per inverter for the DC strings coming in from the PV modules. This is this little grey box here and this little white box up here. These are the various feeds in either from the dual generators. So it comes out of the automatic transfer switch into these boxes, out of these boxes into the Solex box, and out of the Solex box into the main distribution board, which is actually just over here in this second room. And it looks more complicated on the single line drawn. It's actually a nice, neat, compact. That room is no bigger than 3 meters long by about 1.5 meters wide. So everything is nice and compact, and it just looks an awful lot bigger on the single line drawn. The diesel generators are at the back of this wall here. They're in their own room and they're very noisy, so we kept them out there. They were installed out there, and we didn't go change them, but that's where they are. You can actually see cables coming in through the wall here into this box, and then back out to where they need to go. So that's kind of the on-site setup and the installation. And this plug with this loose wire, we've tidied it up since I think. That's the 4G router that we can remotely control it. The inverters also have a display on them, so you can actually flick through and see what every individual inverter is doing, and correspond that then to your commissioning and check on the batteries as well. So it just means that even the maintenance guys on site can come up and just, if they don't have an app or there's no mobile phone signal, they can physically check the system on site. So going on to the next section, apologies. Yeah, so the next section, this is just a graph of 2 days. We commissioned the solar system on the 19th of August. So it's not running for years yet, but the 19th of August is when it was commissioned. You can see the 2 different graphs here, which explain the 2 kind of different operating scenarios. Provisionally, the system should run on solar and battery. But as I said earlier, we're not in the Middle East here. So solar and battery isn't going to be working on 24th of December. Okay, that's why we have the diesel generator. Now, on a good day with solar, this blue line, so this blue line here, that's the battery state of charge. Okay, so you can see in the last couple of days before the 12th of the 9th, the solar or the batteries have been fully charged, even during nighttime. And you can see the load draw here, which is the kind of reddish line here on the top. So she's about 5 kilowatts peaking there at 6:40, 7 o'clock, where the heat pumps all kick on to give that boost of heating in the morning. And then she's steady all the way through. Another kick just before the evening, and then she goes up to the 10 kilowatts for a good portion of the night, especially as we move over here into the 26th of October. This blue line here is the state of charge of the batteries. The yellow is the solar. So you can see the solar even in the September there, the 12th of September, she's starting at 7 a.m. That's that east-west facing system. That's the difference. She's coming up here and she hit a peak of 100 kilowatts, but we didn't need the 100 kilowatts to be produced. So you can see there when the batteries were fully charged, the solar drops down. Now you can't see it here because I have all the filters on to talk about multiple things, but the solar, you can see this blue line, this kind of blue underline here with these peaks, that matches the load here. That's when we were running on battery. The solar then kicked in. The solar took over the load, but it also charged up the battery. That's the height difference between this dark blue and yellow. But then over here, the batteries were fully discharged or fully charged to 100%. You can see that by the state of charge line over here. And then the solar reduced, even though the solar could produce 50 kilowatts that's 11 a.m. It could continue to produce 100 kilowatts, but the on-site load doesn't need it. So we can't just pump 100 kilowatts into a place that isn't going to use it. So that's what's called export limitation. We then reduce the solar capacity via the inverters to match the on-site load. So that's why you see down here, you can't see the yellow because the yellow is matching the on-site load. You can see why it's just a slightly different color to what the load is over here. That's the solar matching the load. And even in September, that solar was still running all the way up until 8 p.m. That's the difference on an east-west facing system. They don't have the massive peak during the day, so why install? Just because you can get extra kilowatt hours doesn't mean the client needs it. And it's something that everybody that's looking at solar or anyone that's designing new buildings, even if it's far lead or anything else, just to get the kilowatt hours, doesn't mean it's actually going to do what the client needs it to do. You should always be trying to match it to their on-site load. The counter to that then is what happens when we don't have enough sun, we don't have enough battery, and we still need the power down below. So that's where this comes in. So to run through, this blue line here is the batteries, and it actually comes down here and it runs just like that. So what that means is here you can see at midnight she's running on the batteries until about 1:20. Now the battery state of charge percentage is shown over here, and that's your 20% line. If you come over here, you can see the batteries are just off 20%, or probably just hitting 20%. And then this red line kicks in, and this red line is grid power. Now, grid power in our instance here is the generator. You'll see up here, we have grid power. No generator came on that entire day. We didn't need it. Down here, batteries have gone down to 20%. It wasn't a great day for the sun the day before. God knows September or October wasn't great. So the batteries discharged to 20%. They did everything they could have. As I said, we have the safety factor. We don't want to discharge past 20%, especially in the first, I think 1,000 cycles on the batteries. So we may change the settings later on, but right now we're quite comfortable with where they are. And you'll see the percentage of generator running in the next one. The generator then kicks on. So up here, up until 12 o'clock, you can see the site load it peaks at 10 kilowatts. It's probably around 8 kilowatts there. The generator then kicks on, and the generator's at minus 20, because what it's doing is it's charging up the batteries as well as supplying the site load. It then charges the batteries to approximately 40%, I think it's about 38.5, and we kicked off generator. Again, we don't charge the batteries up anymore because we're hoping the sun is going to come out and charge the batteries, that there'll be enough if we charge the batteries to 40%, which you can see just here on this blue line where the batteries charge up, we're hoping the batteries will last long enough until the solar comes in and tops up the batteries. And that's what you can actually see happens here on the 26th. I picked a good day for the presentation. So we charge up to the 40%. The battery then starts to discharge again. As it gets down to 30, it's up here at 9:20, or sorry, you can see the solar actually starts there about 8:30. And that's when the solar starts charging the batteries. When the heat pumps come on here at 10 o'clock in the morning, because they're temperature driven, right? So they came on here at 10 o'clock. The solar couldn't meet the load, so the solar and the battery were providing at this point. And then the heat pumps kicked off. The solar jumped up here in yellow, but you can see it was charging the batteries here, mainly charging the batteries because the site load was low. And as throughout the day, you can see the batteries charged up to 60%, and then we're discharging after the solar finished there about 6 o'clock on the 26th of October. If that was a south-facing system, you'd be finished about 4 o'clock. So you get the extra 2 hours. So, and that's how the system is set up, and that's how it works. So sometimes in late December, early January, the generator is going to kick on twice a day. And that's because the batteries are going to charge up to 40%, they're going to discharge to 20, and then it's going to kick on again because we're going to have less solar hours. But what we're going to do is we're going to monitor it. We may change the 20% safety band down slightly to extend it, but until we see how the system is performing, it's very hard to model when your heat pumps are done off temperature and they're offshore they get a breeze, they could go on. So we have it modeled as best we can. What we do know is that the modeling is matching we're outperforming our model despite the bad weather in October. So we're actually getting more kilowatt hours out of the solar system than what had originally planned. So on the next slide, you will see the benefits and the impacts. So as I said at the start, generator ran this site for years and with no solar or anything else because the wind was decommissioned or failed or end of life. So we now have since the 19th of August up until yesterday when I put this graph in, we've only used the diesel generator 14% of the time. And most of that, I think 8.5% of that was in the last 5 weeks. So we got a very, very good run. There has been 10.46 tons of CO2 avoided by the solar, let alone counting in the knock-on effects of not needing a barge or diesel trucks to come out and fill. They haven't got a single fill of diesel since. Now they do have a 5,000 litre tank, so they'll be a while before they need the diesel. They have. This is just the calculation here. At 10,000 or 10 megawatt hours, basically 10.493 megawatt hours of solar produced to date. There's a calculation there which I've included at 0.5 a litre a kilowatt hour. We saved 6,000 litres of diesel for 10.46 tons. The estimated savings to date is just under 11,500. Payback on the entire system is 2.6 years, and we are outperforming the model. The next phase of this is when we run down the diesel tank, is to put in biodiesel or HVO. So that we won't be reducing the diesel generator usage, not just yet. That's hopefully stage 3 when we get more time to look at the hydro generator. But this will at least reduce the carbon footprint on the island further. So it's a very good fuel. I won't get into it too much here because it's not done, but you can do very little minor modifications, if any, depending on some of the modern diesel generators on sites. I've been asked a couple of times recently by developers how they need the redundancy of a diesel generator or a traditional diesel generator, large-scale batteries to provide bank backup and things like that for some that are being built in Dublin are very expensive, and they have to be explosion proof rooms and all this good stuff. These days you can install diesel generators, you just run them on HVO. So what it means is you can still provide a green solution to your clients with a diesel generator. It's just there's no modifications required for Cummins or any of those newer type generators. Most of them are built to take dual fuel, so it's just another consideration that people can have when they're designing new buildings and need a UPS system. You mightn't actually need 2 ESB incomers for redundancy. You can get away with other solutions if you just know the technology that's there. That's all I have on my presentation, I suppose. The next is questions and answers. And yes, this photo was taken the same day, and that's the same island. And it's just, we are very, very lucky on the day. So thanks everybody for listening. I appreciate Engineers Ireland giving me the opportunity and the support for it. And if anyone has any questions, I'm here.